Thank you. So I'm going to talk about how we can explain high wintertime ozone events by using the state-of-the-art three-dimensional air quality model. First of all, I would like to acknowledge my co-authors from CU Boulder and NOAA. In this first slide, what you see is this is measurement site in Utah, the Uinta Basin, during winter of 2013. And today I'm going to show you some data from this measurement site. So, as you know, in recent years, high wintertime ozone episodes were experienced in rural areas, in Wyoming and then in Utah, where high oil and natural gas production takes place. In fact, during last year, within the entire United States, the highest ozone concentrations were observed not in urban areas, in rural area during winter time in Uinta Basin. So far, air quality models have been unable to predict or to reproduce these high ozone events. And NOAA and other research organizations conducted intensive field campaigns in 2012 and 2013 over Uinta Basin, Utah, to study meteorology and chemistry. And today, in the previous session, Jessica Gilman also talked about, she showed some data from those field campaigns. Interestingly, in 2012, it was warmer and no snow, and consequently, no high ozone was experienced. In contrast, 2013 was snowy, colder, and very high ozone concentrations were observed. So what we did, we used a coupled meteorology chemistry air quality model, WRF-Chem, to simulate both these time periods. Now, what's the geography of this Uinta Basin? As you see, Uinta Basin is quite a large basin. It's surrounded by high mountains, and it's located in northeastern part of Utah State. And the basin is sparsely populated. There are about 50,000 people living here in this region, and therefore the urban emissions are not very high. However, there are about 10,000 oil and gas wells, as you can see with these dots. And during these field campaigns, 3 surface measurement sites were deployed, mostly horse pool. I showed you the picture of the site. And the highest nitrogen oxide emission source in the region is this power plant. And you can see its photo taken during 2013. Now, what we did, first of all, in order to conduct the air quality modeling, we built 2 emission data sets. First emission data set is based on EPA NEI 2011 emission inventory, which is the emission inventory used for regulatory purposes in the United States. Here in this row, I show total methane, non-methane VOC, and nitrogen oxide emissions for only oil and gas sector for the Uinta Basin from NEI. Then, we also built our emission data sets using atmospheric measurements, so-called based on top-down approach. So for methane emissions, we used Anna Karyon's numbers. She estimated methane emissions from part of the basin using 1 day of flight during 2012, so-called mass balance approach. And then, at the surface site, hospital site, NOI and different non-methane VOCs, they correlated very well with methane. So by performing a regression analysis, we estimated different VOC emissions and also NOx. Here you can see the numbers. The bottom line here is VOC emissions, including methane, are significantly underestimated in the EPA inventory for the oil and gas sector. In contrast, NOx emissions are about 4 times higher in the bottom-up inventories than our top-down estimates. Now, if I use those emissions, plugging in our model, what ozone mixing ratios the model predicts or simulate our simulation results. Here, what you see is time series during end of January, February 2012. You may be wondering why I use this scale, because in 2013, the ozone mixing ratios were very high. What you see in 2012, as I said, no high ozone cases were observed. And the different model scenarios where I plotted NEI 11 and top-down, and the case where I removed all the oil and gas emissions from the inventory, they all yield very similar ozone mixing ratios for daytime values, basically indicating that during 2012, these emissions don't result in high ozone events because of different meteorology and also lack of snow cover in the area. And what you see is just variability of ozone around the background value, which is 40 ppb. Now, 2013, what you see in black measurements, as you see, the mixing ratios are very different, sharply contrasting the 2012 values. What you see here is end of January, beginning of February, there is day-to-day buildup of ozone during stagnation episode, and then storm came, the basin was cleaned up, and then another stagnation episode. Here in blue, I show model results using NEI inventory. As you see, none of the ozone events were captured by the model. If I use our emission estimates in red, we get completely different results, where the model can reproduce very high ozone mixing ratios, such as 120 ppb, and also this cleaning time period where the basin was cleaned up and then another stagnation episode. And there are nighttime biases. This is not due to chemistry or emissions. I will show on the next slide. It's due to the strong drainage flows near surface. There's another also model case here, where again I removed all the oil and gas sections in green. And the difference between the green and red lines indicate how much these oil and gas emissions contribute to high ozone events. So basically the green line shows what we would have seen without this oil and gas sector in the basin. Basically small variability around 40 ppb background ozone in winter. Now, how the ozone distribution is simulated in the model. Here I show vertical cross-section in west-east direction along Uri and Horspool surface sites. What you see here is the depth of the basin and its horizontal distance in longitude, wind vectors, and ozone mixing ratios. So this is early morning, 5th of February, one of high ozone days, and this is afternoon. As you see in early morning, we have high ozone above ground, which is ozone residual layer from previous days. Now, there is, as I said, strong drainage follows near surface, which bring cleaner air to the basin, but ozone, the basin is not cleaned up. The ozone and other pollutants mostly stay in the basin and they get trapped and build up. Subsequent days build up occurs. Now, during the afternoon, ozone is transported back to the Horspool site, but there's also new ozone production. So what you see here, about 120 ppb ozone during the daytime. And also what's interesting here is the boundary layers were very shallow, so the ozone is confined to about 100 meters deep boundary layer. Also there is this depletion of ozone. This is because of Bonanza power plant titration by NOx. Now, how is realistic is these model simulations? Fortunately, we had tetrazone measurements conducted by NOAA group, where I took 8 profiles, vertical profiles, for the same day and interpolated in time and space. On the left, the measurements, on the right, the model. As you see, the measurements confirm very shallow boundary layers, 100 meters deep about, and these high ozone concentrations exceeding 120 ppb. Also, there is ozone above the boundary layer. But as you see in, over the boundary layer, aloft, there isn't much ozone, so basically there isn't any transport of ozone coming from outside of the basin. There is this titration again because of Bonanza power plant. Now, we did different multiple sensitivity simulations where we zeroed out or eliminated different processes or different emissions to study the sensitivity, the contribution to ozone production in this area. And here I show so-called impact factor. What does it mean? Basically, 100% means if we remove that process or emissions, all the enhancements that model predicted is gone. So basically, the model doesn't predict any ozone above the background. Okay, what's interesting, if we remove snow albedo effect on photolysis, but keeps the metrology the same, all the effect is gone. So meaning that this enhancement in photolysis rates due to high albedo is very important, crucial to get these high ozone events. Then there's another effect of snow. Basically, when there's a snow on the ground, the deposition is reduced. So loss of ozone to the ground, which is about 50%. So this has to be taken into account as well. Then we did emission reduction model cases, which shows that ozone in this area for this time period is not sensitive to NOx, but is very sensitive VOC. And what's interesting, that it's very sensitive to aromatic emissions. So basically, the contribution of aromatics and alkanes are about the same. However, alkane emissions are about 10 times more than aromatic emissions. So basically, there is this disproportionate influence on ozone by aromatic precursors. Okay, in summary, I want to say that as you have seen, different emissions, such as greenhouse gas emissions, methane, and non-methane VOCs and NOx, these ozone precursors, those emissions in the bottom-up inventories can be significantly improved by using top-down estimates. The model is able to simulate high ozone only by using our top-down estimates, not the bottom-up EPA inventory. And also the sensitivity simulations show that reduction of VOC emissions would be very efficient to mitigate this ozone problem in the Uinta Basin. And the model results tell us the high ozone in the Uinta Basin are primarily caused by the very high VOC emissions versus NOx emissions from the oil and gas sector. This is very different than urban areas. Persistent stagnation episodes, and high surface albedo, and reduction in deposition due to snow cover. And we published these results in a paper you can find in ACPT, and it will be available in ACP soon. With this, I would like to end my talk, and thank you for your attention.
We have about a minute or so for questions.
We discussed these results with this Utah group. You can simulate high ozone, not very high, but relatively high, if you take NEI emissions with VOC profile, which has a very high formaldehyde emissions. I would like to stress, this is a good question. Please note that NEI inventory contains, as far as I know, VOC speciation profiles, accurate profiles, or more realistic, only for the basins where West Jump provides. If you use those profiles with high formaldehyde, you may get some ozone, but those profiles are for, I believe, for flaring, so they are not realistic. We discussed that, and I think there is this agreement that we should use more realistic VOC profiles. So, thank you.